Hi, my name is JK, and my full name is Jacob. That's it. Hi, I'm Wei.
Hi, I'm Yumi.
Hi, my name is Gavin and I'm single.
Hi, my name is Morgan.
Talk about wireless power transfer. So the concept of wireless power transfer. So what is wireless power transfer? Wireless power transfer is a transmission of electrical energy without wires as physical link. In wireless power transfer system, a transmitter device driven by electrical power from a power source generates a time-verified electromagnetic field that is capable of transporting power across space to a receiver device, which extracts power across space to a receiver device and supplies it to an electrical load. So there are two types of wireless power transfer techniques, non-radiative and radiative, but in this video we are going to talk about non-radiative techniques, which is only used in short distance. When using non-radiative techniques, power are transferred through short distance by magnetic field using inductive coupling, which is between wires, or by magnetic field, which is called as captive coupling. So inductive coupling is the most widely used wireless technology, like handphones or car batteries, which my teammates will show it later. So that's it for the concept.
So today I would like to talk about the Faraday's law concept behind the wireless power transfer. So Faraday's law states that the EMF given is given by the rate of change of magnetic flux. So be careful that it's not the magnetic flux itself, but the rate of change of magnetic flux. The term wireless power and power through air in wireless power transfer are relatively modern. The physics behind them is fairly established by Maxwell equations that were formulated in 1862. In particular, there is Faraday's law of induction that states that in case of harmonic oscillation, so the voltage induced in a closed circuit is proportional to the magnetic flux it encloses. In practice, it means when you have two coils, the magnetic field from the first coil that it will transmit to the second coil to receive it and induces voltage in it. Just like this diagram. The diagram from the first coil, where the magnetic field that produced by the coil will transmit to the coil and the coil, which is coil A. So this causes voltage to appear in the second coil, which in turn causes there will be current flowing in the second coil. The current then flows through the load that connected to the secondary coil. Maybe here, secondary coil. For example, there's a bulb. It will flow through, and then voltage EMF will be induced. Therefore, this bulb will light up. Then we can say that there is a power transfer between the two coils. As we all know, magnetic fields are invisible. You cannot see this field in real life. So how can we visualize the processes taking place during the wireless power transfer? We have an experiment that can help us to visualize the processes taking place during the wireless power transfer. So it's actually just by positioning the two different coils with different distances. So how do we visualize the process taking place during the wireless power transfer? we can actually do experiment. There are tools that can help us to visualize the processes. So it's just by positioning the coil at a few distance. First, you put two coils with a distance of maybe 7.5 cm. For example, 7.5 cm. And here will be connected to a bulb. And then another one, we distance it about 10 cm. And also connect a bulb on it. Third, distance is 15 cm. Connect a bulb to it. So this one will be a receiving. This three will be a receiving coil, and this one will be a transmitting. From this experiment, a result can then be generated to show that the magnetic field around these two coils and demonstrate the input power and deliver power, and also the efficiency for a certain input voltage. Magnetic field around each coil is proportional to the current that flows in it. So the observation that we can make from the simulations are actually when each coil are closer to each other, the more efficiency is the power transfer between the coil. In other words, higher percentage of input power reaches the loop here, the loop in the receiving coil. So you will see that the bulb will be brighter, and with a further distance, it will be dimmer, and even further, it will be more dimmer. It will be like brighter and dim and more dimmer. It's because that when it's near closer to each other, the rate of change of magnetic flux, is the rate of change of magnetic flux is higher. So as it is further, the rate of change of magnetic flux decreases. So we can see that the delivered power will be in the secondary coil will be more when it's shorter distance, and when it's longer distance it will be lesser and lesser. So these are the things that we can see by the Faraday's law concept or theory behind the wireless power transfer. Thank you.
One of the examples of wireless power transfer in real life is wireless charging. Wireless charging is the transfer of power from power outlet to device. As the name suggests, you don't need to plug in a cable to your phone to charge your phone. Then how is it possible? Well, wireless charging is not truly wireless. You still need a wire to provide the energy. The difference is that the wire is connected to a charging base instead of your phone. So you can just drop your phone onto the charger and your phone will charge. Basically, how wireless charging works is by transferring energy from the charger to a receiver coil in the back of the phone via electromagnetic induction. First, there are two induction coils involved. One is the transmitting coil in the charger connecting to the power source. Another one is the receiver coil in the back of your phone connected to the battery. The current coming from the wall power outlet moves through the wire in the wireless charger. In the wireless charger, this energy is converted into alternating current within the transmitter itself. This alternating current energizes the transmitter coil, causing the coil to generate a magnetic field. When the receiver coil in the phone comes nearby, it does not necessarily come into contact with the charger. As long as it is inside the range of the magnetic field, The receiver coil will take power from the magnetic field and convert it back into electric current to charge the battery. The two induction coils in proximity combine to form an electrical transformer. Wireless charging relies on magnetic field. The disadvantage is that it often has a short range of effect.
The next example I'm gonna give is for cars. Now, how does wireless electric vehicle charging works? Charging cars without wires works in a similar way to the wireless phone charger, just on a bigger scale. Using a technology called inductive charging, electricity is transferred through an air gap from one magnetic coil in the charger to a second magnetic coil fitted to the car. All you have to do is park in the right place so the coils are aligned and charging will begin. I will show you a video on how it's done.
BMW is the first car manufacturer providing wireless charging for your BMW 5 Series i Performance. It's the comfortable way to charge your BMW plug-in hybrid. Blue lines in the center display guide you to position your BMW above the ground pad. As soon as a green circle appears, you are directly over the charging plate. When you switch off the ignition, the charging starts automatically. And this is how it works. The primary coil in the wireless charging station generates an electromagnetic field. The secondary coil in the car then transfers the energy to the high-voltage battery pack. A completely empty battery is fully reloaded within 3.5 hours. BMW wireless charging makes charging easier than refueling.
In this video, I will show you how wireless power transmission works. These are the materials for the experiment. First of all, we need to make one emitter coil and a receiver coil. For this, we need to prepare a cylindrical object with about 4 centimeters to make the coil. Then, we take the wire and make 12 turns around the object. After that, we have to make a loop for the emitter to have a center point for the coil. Then make another 12 turns. Okay, now cut off the wire when it's done. And now we have 3 connecting points in the coil: the starting point, the center point, and the ending point. So after that, we can finish off by putting some tape on the coil to avoid unwinding. This is the receiver coil, which is made in the same way as the emitter coil without the loop with 24 turns. And it is connected to a LED in the 2 end points. Okay, here we have a diagram on how to make a complete emitter coil with transistor. First, center point is connected to the positive terminal of the battery, and the 2 other points are connected to the base and collector of the 2N222 transistor respectively, and the emitter of the transistor goes to the negative terminal of the battery. Okay, here's the emitter coil and the receiver coil. A AA battery. Okay, complete the circuit to make a magnetic field around the emitter coil. Then move the receiver coil
toward the emitter coil. As you can see, when the receiver coil is placed within the magnetic field produced by the emitter coil, it will cause an electric current to flow through it and light up the LED. This is because the magnetic field has transferred electric power from one coil to the other coil. Then, try to place a cloth between the two coils. The LED will still light up because magnetic field can still move through obstacles and produce electric power. This principle is called induction.